Hello and welcome. In this video, we're going to take a look at gradients and the directional derivative. So to motivate this concept, let's suppose you are hiking and you are 2 miles east and 3 miles north of the trailhead of a mountain hike. If we define x to be the distance traveled east and y to be the distance traveled north, both in miles, and thus, if z equals f of xy is the elevation of the mountain in feet relative to sea level, then we want to be able to answer some questions about this. So first of all, let's visualize what we have. What we have is we have our x and y axes, which represent the distance that we've hiked, represented in miles. And here we are at a point located 2 miles east and 3 miles north of the trailhead. And our elevation at this point 2, 3, the associated elevation is given to us right here as 1,000 feet. So where we stand right now, the elevation is 1,000 feet when we're 2 miles east and 3 miles north. So we're given some information here. Well, one is the actual elevation. And the other bits of information that we have are partial derivatives. So let's think about what this means for a second. F sub x would be the same thing as saying df dx. And we know that that value is equal to 500. And specifically, this is at the point 2, 3, but I'll omit that notation here. So we could write this as 500 over 1. When we think about what this means, we need to look no further than to analyze what does f measure. Well, f measures the elevation in feet. So the denominator, which measures the distance traveled east, that is in miles. So the way we can interpret this is we can say that if we were to travel 1 mile, one additional mile east from where we currently are, that is 1 more mile in this direction, then what we would expect to see is an elevation increase of 500 feet. So we would no longer be at 1,000 feet, but we would be at 1,500 feet. In a similar fashion, we could interpret this guy as well, and we could say that since this is really df dy, which is 700 over 1, well, f is still feet, y is still in miles, it's just in the northern direction. So that we could interpret to mean if we traveled 1 more mile in the north direction, what we would expect to see is a 700-foot increase in the elevation. So depending on which of these two directions we pick, we either gain, we have a change in f of approximately, now this is based on a partial derivative, so we can't say that the change in f will be exactly 500 because that mountain is likely not doesn't have a linear slope. But if it did have a constant rate of change, we would say that the change in elevation should be about 700 feet. However, if we take it in the eastern direction 1 mile, we should notice an elevation change of about 500 feet. Now, we're going to be able to answer some questions about this. So now that we have made sense of what all of this data means, we can now choose to travel along each of the following vectors. And what we want to do is we want to estimate the elevation at that new point. So if we travel in the direction of the 1, 0 vector, well, that's precisely traveling 1 mile east. So this is the 1, 0 vector. It looks like this. It's a horizontal vector. It's really just this vector right here. And so we want to estimate the elevation at the new point. Well, to get the elevation at the new point at what we would call f of 3, 3, so now we'll be 3 units east and we'll still be 3 units north. Well, we have to say that that's approximate because we're going to be using a partial derivative, but we need to analyze. Okay, so the change per unit in the x direction is 500 feet per 1 mile, multiplied by how many miles we travel in that direction, which is given to us as 1 mile. That's this value here. And now we could repeat this process and say, well, we would also realistically need to add to that the displacement that we would expect by going north, so 700 feet for every 1 mile, multiplied by how many miles we go north, which is actually 0 in this case. And so we're really just putting the 0 here for completion. So you can see that what this really is representing is very similar to the idea of a differential. And so this value will come out to, what we would need to add to this actually is, this is just going to give us, how about we write it like this? Well, this is really the change in elevation that we're estimating here. We're going to see that this comes out to 500 feet. As you can see, the units, the miles are all going to cancel, and it will just be left in total feet. And that's just the elevation change. So to indicate that this is an elevation change, but it's in the direction of this vector x. So what I'm going to do is I'm going to put a subscript of x with a little vector hat. So this is no different than saying f sub x or f sub y. These two notations denote the change in f by moving 1 unit in the x direction, the change in f by moving 1 unit in the y direction, and now this kind of new updated notation, the change in f by moving 1 unit, or by moving in the direction of this vector x. So we get 500 feet, and now we can put this together and say, well, this is the new elevation, f of 3, 3. That's the actual elevation. We approximate this to be where we were, which was 1,000 feet, plus the 500 feet that we just gained by moving in that direction. So we should be at an elevation of 1,500 feet, as we kind of described intuitively here a moment ago. Now the same kind of idea applies here. If we want to estimate the change in elevation by moving in 1 unit, or moving in the direction of this x vector. Oh, and by the way, right here, I should not have written 3, 3. This is the rate of change, and this was the rate of change associated with the point 2, 3. So before we split this up into 2 pieces, this here estimates the new elevation. This here estimates the elevation change. Okay, so f sub x at the point 2, 3 for this new vector is going to be approximately, well, it's still 500 feet for every 1 mile we travel east, multiplied by how many miles we travel east, which in this case is 0 miles, plus how much our elevation changes by traveling in the y direction, which is 700 feet per 1 mile, multiplied by how far we travel in the y direction, which is 1 mile. So our elevation change should be, in this case, 700 feet. Which makes sense because that's exactly what the data that we were given describes. And now to calculate the new elevation, which puts us at the point f of 2, 4, we're still at an x value of 2, but we bumped up our y, our northern component by 1 unit. And so this is going to be our original elevation at the starting point, 2, 3, added to the elevation change, which is 700 feet, giving us a new elevation of 1,700 feet. Just, again, an approximation because we're using an instantaneous rate of change to do this. Well, there's no reason that we have to travel in just the I or j directions. So recall that really this vector right here is the I vector. It's the 1, 0 vector. It's the unit vector in the x direction. And that this here is the j vector, the unit vector in the y direction. Where we actually perhaps want to travel is to cut across the plane. Rather than to travel just east or just north, we often want to travel in both directions. So the vector 3, 5, thought about what that would look like. We could say, well, 3, 5 would mean 1, 2, 3 units to the east and 1, 2, 3, 4, 5 units to the north. So if we put these together, our new vector, which I'll do here in orange, will put us at a location that would be over here. And that's what we're looking at in this situation. So if we were to do all that displacement, we can see that our formula is not going to change, that our approach to solving this problem is still going to be to say, well, the change by moving in the direction of x, the change in f by moving in the direction of this vector x, while we're at the point 2, 3, that's where we start, that's our 2, 3 point right there, that's going to be approximately, excuse me, once again, 500 feet per 1 mile east. In this case, we're traveling 3 miles east, so we're going to, if this were a constant elevation change for every 1 mile, then we would get 1,500 miles of elevation increase just from moving in that x direction. Plus, now we need to account for the y direction, which is 5 miles. And for every 1 mile, we gain 700 feet of elevation, multiplied by those 5 miles. And that's going to give us a new change in elevation, which we'd expect to be much greater because we're doing displacements in both these directions. So 1,500 plus 3,500 will give us 5,000 feet of elevation change. So to calculate our new elevation, which would put us theoretically now at the point, well, we were at 2, 3, we displaced 3 miles east, which puts us at a position of 5 units in the east direction. 1, 2, 3, 4, 5. And we're all the way up here at 1, 2, 3, 4, 5, 6, 7, 8, which is our y position of 3. Add 5 to that puts us now at the position 5, 8. So our new elevation would be where we were at the point 2, 3, which is 1,000 feet of elevation. But now we've gained 5,000 feet of elevation, and so that should put us at 6,000 feet. Now, if this looks very, very familiar, it really should. We still have, if we kind of piecemeal this quantity here was f sub x at our starting point, which is 2, 3 in this example, multiplied by how much we stepped in that direction, plus the rate of change in the y direction, f sub y at the point a comma b, multiplied by our change in y. And this gave us, in this case, the change in f by moving in the direction that we moved in while standing at the point 2, 3. And again, this was an approximation because we used partial derivatives, but our changes in x were not, and changes in y were not infinitesimally small. So this is starting to reappear here. The new component in what we're witnessing is the fact that now we have a direction that is not strictly in x or strictly in y, but instead in the direction of some vector, which was here our orange vector. We decided to cut across the plane. So let's take a look at one more example here. In this example, we are shown a contour plot of the temperature in degrees Celsius. So we see we have this contour represents 50 degrees Celsius. This contour, the temperature is 45 degrees Celsius and 40 and 35 degrees Celsius. At the point x, y, that's some measurement which is in meters, and y is in meters as well. Estimate now this is not the new temperature, this is the average rate of change of temperature as we walk from point A to point B. So we need to collect some data first. To put this into a more manageable context, we see that at point A, we're standing at the point, these are increments of 25, so 125, 200. So at 125 meters east, 200 meters north, we have a temperature of 45 degrees Celsius. At point B, we are at an x position of 25 meters from the origin and 225 meters above the origin with a temperature of 50 degrees Celsius. So we have x, we have y, and then we have our z value. So to estimate this rate of change, first of all, we can see pretty quickly that the change in temperature, here is, we went from A to B, so we gained 5 degrees Celsius. Now the challenge is, if we want the average rate of change, the kind of quantity that we're looking for is the temperature change divided by the distance change. So to calculate the distance change, we can't just look at the x component or just the y component. We actually have to look at how long this vector is right here. So to calculate the length of that vector, I can triangulate it. So I will go ahead and form a triangle here. So there's my triangle. And this component right here is, well, negative 100, really, if you represent it as a change. It's a change of 100 units to the left. And this one right here is a positive 25. So to get the length of this, we can apply Pythagorean Theorem. So we'll call this vector right here AB with an arrow over it. So it's from A to B, it's a vector. And so to get the magnitude of that vector, in other words, how long is that walk, we have to take the square root of the sum of the components squared. The negative I don't really need there because it's going to get squared anyway. And that is going to come out to, let's see, about 103 meters. Now that is in meters because if x represents meters, y represents meters, then the square root of meters squared plus meters squared is going to still be in meters. So we traveled a total of 103 meters, and we obtained a 5 degrees Celsius temp change. So as we begin putting this together, we could say in a very basic format that the change in temperature per change in meters would be 5 degrees Celsius positive divided by 103 meters, which comes out to about 0.05 degrees Celsius per 1 meter. Great. Well, so now that we know that on average every meter we were getting a temperature increase of 0.05 degrees Celsius as we traveled from this point along this vector, every meter that we advanced, we should have noticed about a 0.05 degrees Celsius change. Of course, that's probably not the case. You don't walk 1 meter and suddenly the temperature changes by exactly the same amount, but this is the average rate of change. Average rate of change. Now, one other way to think about this is that what we've really calculated is the directional derivative, or the derivative in the direction of the vector AB. So this is an estimate of the derivative in the direction of AB. Again, we've used distances that are not exactly infinitesimally small, but this average rate of change is perhaps our best estimate only because we have no contours between 45 and 50 to kind of shorten that distance a little bit. So if we put this together and we use some of the notation from above, we've kind of described, that f sub x at a point AB is the instantaneous change in f per change in x. We've written that f sub y at a point is the instantaneous rate of change in f per unit change in y, of course, at the point AB. And so in general, we like to write from this, we like to extrapolate and say that f, or the rate of change in f in any direction at a point, could be written as the change in f per unit change in direction at the point A, comma B. Okay, well, our direction, in this case, was f sub AB. So if we write f sub vector AB, that's similar to our notation in our previous example, where we're saying the rate of change of temperature per unit change in the direction of AB, the vector AB, at some point, little a comma little b, is the rate of change in temperature per change in the direction of AB, standing at the point little a, little b. The capital A, capital B, little b are in no way connected. And so to calculate this, what we did is we took the difference in temperature, which was 50 minus 45 degrees Celsius, and we divided this by 103 meters. Now, to make this more general, we could say that this was the change in F. The change in F divided by, we should have said approximately here because we're approximating this, divided by, well, 103 meters was really the magnitude of the vector AB. So we're just creating a more mathematical definition here. Now, that can be written as f sub x at the point a comma b. In other words, if we had more information, if we knew the elevation change per unit x and we knew the temperature change per unit y, then we could have constructed something similar to this, where we could have seen the temperature change due to each of the two components. So even though we don't have the partial derivative with respect to x, I'm still going to go ahead and write it this way. And then we multiplied this by the change in x, plus we took the rate of change in the y direction. Again, this is not a quantity that we had. We had to just take the magnitude of the vector and know what the temperature change was overall. And we multiplied this by the change in y. And then we had to divide this entire thing by the total distance. Okay, great. So I'm running out of space here, so I'm going to move over to this side here, and let's kind of continue on building this thing out. So the total distance is really, and AB, the vector AB, what it contains in it is the change in x and the change in y. And we already estimated that. We described that to be negative 100 and positive 25 for the two components of the AB vector. And then we had to divide by the total distance. Well, the total distance is really just the magnitude of the AB vector. So if we piece these things together, and what we're coming up with here is the F sub AB, so the change in temperature due to travel in the direction of AB, to calculate that average rate of change, at this point, that's approximately given by, well, if I'm dividing by, if this right here is really the magnitude of AB, then I could apply that magnitude to each of the two terms. When I divide a fraction by, I could divide the first piece of that fraction by AB and the second piece of that fraction. So this is what it would look like. We would have f sub x, a comma b, multiplied by delta x divided by the magnitude of AB. Remember, when you divide a product by something, you don't divide both factors by that. You divide either one. So, for instance, if I took 3 times 4 divided by 2, I don't divide 3 by 2 and 4 by 2, because this is really 12 divided by 2, which is 6. But I could take 3 times 4 divided by 2, that would be 3 times 2, which is 6. Or I could take 3 halves times 4, 3 halves is 1.5, 1.5 times 4 is 6. And then the second term, f sub y at the point a comma b, multiplied by delta y divided by the magnitude of AB. Okay, well, what this really does is we've just taken the components. This is the component of of AB divided by magnitude. And so is this over here. This is the same thing. So when I take components and I divide the components of a vector by their magnitude, what I end up with is a unit vector. If I take a vector and I divide it by its magnitude, I get the unit vector. So these are components. This and this here are components of unit vector. Now, why does that make sense that it should be the unit vector? Well, what I'm ultimately trying to determine, or what we calculated here, was we didn't want to know that the temperature changed by 5 degrees. What we wanted to know was how much did the temperature change by, on average, for every 1 unit meter change in the direction of travel. So it makes sense that what we've done, and we kind of did it intuitively here, we naturally knew to divide by the distance. Mathematically, it still pans out that way, that we're going to divide both of the components by their magnitudes. And so what that will do is that will give us a unit vector in the direction of AB. So to write that a little bit more formally, it follows from the above examples, and we're going to define this now, that a directional derivative, this is not really anything new other than we're not limited to travel in only the x or only the y like we had earlier. We don't just have to travel 1 unit this way or 1 unit this way. There's no reason why we couldn't simply travel in that direction, for example. So here what we're going to have is travel in some arbitrary direction. We'll call that the directional derivative. In other words, how much does f change by traveling 1 unit in the direction of the specified vector. So if we want to move in the direction of a unit vector, a vector that has already been unitized, so if you think about what u is going to be potentially some other vector that we started with, divided by the length of that vector. And so that will produce what we now are referring to as u1 and u2. So if you take the magnitude of this vector, it's going to have magnitude 1. And we want that because it would be like going into a gas station and filling up your tank, but you look across the street and there's another gas station that's charging $4 for 1.6 gallons. It would be really hard to decide without pulling out a calculator which one of those gas stations you should go to. So in the same sense, if we're going to compare a bunch of directions, like for example, here's another vector and here's another vector, then clearly I'm probably going to get a larger directional derivative by moving along this vector because it's much longer. So what I'm going to do before I travel in that direction is take all of these vectors and scale them down so that they're all 1 unit long. And what that will allow me to do is basically compare apples to apples. It will allow me to go to whichever gas station I want and always know the price for 1 gallon of gas. Okay, so here we have our first example. Let's calculate the directional derivative. So this could represent, again, some sort of temperature. So let's give it some context. And this will be in meters, and this will be in meters. And we want to travel in the direction of I plus j. So let's do a little bit of mapping here first. Here's our graph. Here's x. Here's y. And we're standing at the point 1, 0. So here we are at the point 1, 0. And we want to move in the direction of I plus j. So above us, here's the z-axis. The z-axis is coming straight out at you on the screen. There's some sort of surface hovering here, and we're standing on one point of that. What point are we standing at? Well, or what's our elevation? Or what's our temperature at that point? Well, f of 1, 0 is 1 squared plus 0 squared, which is 1. So our elevation at this point, 1, 0, is or the temperature is 1 degree Celsius, if we wanted to put it in that context. Now, where are we traveling? Are we going this way, this way, this way? Well, we're moving in the direction of I plus j. Okay, so I plus j, I, remember, is the 1, 0 vector. J is the 0, 1 vector. We're going 1 copy in each of those directions. If we add those together, that's the same thing as saying 1, 1. So whatever your coefficients of the I and j are, those are the components of your vector. So we're traveling 1 unit east, and we're traveling one unit north. So that would mean that our vector u, or our vector, is going to point in that direction. But the problem is that this is not good for comparison purposes to say another direction of travel because its magnitude is not necessarily 1. In fact, it's not. So let's calculate the unit vector in the direction of 1, 1. So that will be 1, 1 divided by the magnitude of 1, 1. So never assume that your vector is already of unit length. If you calculate the magnitude and it's already of unit length, then division by 1 is not going to change the components of that vector. Now, it turns out that this is going to be 1, 1. This is the square root of 2. And so if we divide both the components by that, or alternatively, you could think about it as 1 over the square root of 2 times the 1, 1 vector, well, that will give me components 1 square root 2 and 1 divided by square root of 2. So what we've effectively done here is, with this vector, we have shrunken this down so that we ensure that the length of that vector, or the length of that path, is only going to be 1 unit long. Again, so that if we compared the change in temperature for this vector to that of another vector, then we would be comparing apples to apples. We'd always be speaking of 1 meter of travel. So this pink vector has 1 meter of distance. Now I want to calculate the total temperature change by moving in the direction of u. Be careful how you pronounce this. This is f sub u. And so when we're at the point 1, 0, and we're going to move in the direction of these components, well, the first thing we need is the partial derivatives, f sub x at 1, 0, times u1, which is going to be this component here. That's how far we travel in that x direction. And u2 is going to be this component here. Plus, we need to add to that f sub y at 1, 0, multiplied by u sub 2. So the partial derivatives of this guy are f sub x of xy is 2x, which means f sub x, when you plug in your current point, is going to be 2. And then f sub y of xy is 2y. And since y is 0, f sub y at 1, 0 is simply going to be 0. So the way we can interpret this, if we're dealing with degrees Celsius in meters, that if you step 1 unit in, you're standing at the point 1, 0, and if you were to walk 1 meter to the right, you should notice a 2 degrees Celsius increase. If you were standing at the point 1, 0, and you stepped 1 meter in the direction of y, you should notice no change in temperature at all. In fact, traveling up and down is not going to change your temperature at all, only traveling right or left. So to put these pieces together to get this total change, so we know that 1 unit in the x direction is going to create a 2 degrees Celsius change. Well, how far are we going in that direction? We are going 1 divided by the square root of 2 meters. Plus, our elevation change per meter in the y direction is 0 units, multiplied by how far we travel in that direction, which is 1 over the square root of 2. And this gives us 2 divided by the square root of 2. And if we wanted to add units, this would be degrees Celsius per meter. And there we have it. So we now computed our first directional derivative, which again is just an approximation. We probably should have said this is an approximation because even 1 divided by square root of 2, this vector is not infinitesimally small. It is exactly 1 unit long. Okay, so why would we want to do this if it's not exact? Well, what we've just written, that the change in f per unit change in the direction of this vector u at the point that we're currently standing at is equal to the change in f per unit change in x multiplied by how far we go in the x direction, plus the change in f per unit change in y multiplied by how far we move in that direction, u2. one way we could write it is as a dot product, because we see that two things are multiplied, and they're added together. So really what this here represents, or can be represented as, is a vector containing the two partials multiplied by the two displacement components. So this was 1 over the square root of 2, 1 over the square root of 2, and this is our vector 2, 0. So back up here, if we looked at that, we would say that this was 2, 0 dotted with 1 over the square root of 2, 1 over the square root of 2. We'll see soon why this is a really valuable way of writing it. This guy here has a special name. This guy here is considered the gradient vector. And that's often denoted by this inverted triangle, which you can just read as grad F. And you'll see there's another notation here in a moment that makes that more evident, dotted with the U vector. And this is just a nice compact form, if nothing else. If this had no other application, then we could see that calculating directional derivatives is convenient. It's a dot product. And so U1, U2 is simply the U vector. And an alternative notation, instead of using the inverted triangle, is to write the word grad F and put a vector over that. You'll see some textbooks don't put the vector over that, but I think it's important to do it because it emphasizes that it's still a vector in its own right. And then the U vector has been unchanged. And so notice that these two notations are identical. So grad F, or sometimes people read this as del F. You'll sometimes hear that this is read as del F, and that they read this as grad F. But they both mean the same thing. They are the gradient vector. Now, gradient is a fancy word for slope or steepness. So you might see on roads that you're traveling on that there's a grade. If you're traveling up a mountain, that there's a 2% grade. That's kind of the same idea here. Gradient is essentially slope vector. Okay, so just to kind of get comfortable with this, let's compute the gradient vector. So find the gradient vector of this function here. Okay, and then later on we'll use this bit of information down here. Okay, so our gradient vector, which I'll go ahead and use both notations, the gradient of f at the point a comma b is going to equal the partial of f with respect to x at that point, followed by f sub y at that point. So the first thing I need to do is compute the partial derivatives of this function. And so f sub x of xy, just the general function, the derivative of x with respect to x is 1. The derivative of e to the y with respect to x is 0. That's a constant. F sub y at the position xy is the derivative of x with respect to y is 0. The derivative of e to the y with respect to y is e to the y. And now I can calculate what f sub x is at the point 1, 1. And so that is not going to change regardless of what x or y are. The f sub x's will always be 1. And to get f sub y at the position 1, 1, e to the y, which is about 2.17. So the gradient vector at the point 1, 1, alternatively written as grad f at the point 1, 1, is equal to the vector containing components 1 and 2.17. Very nice. So there's our gradient vector that we've just found. Okay, so we're going to now compute the directional derivative, or ultimately we'll compute the directional derivative. But notice that this vector that we're going to travel in, u equals 3, 4, it's not a unit vector. So don't ever assume that the vector is a unit. As I mentioned, unitize it, calculate its magnitude. If it's already 1, then there's no need to divide it. If its magnitude is not 1, you do have to divide it. Okay, so in its own right, what we've just come up with here is that the two partial values, f sub x and f sub y, form a vector. And that means we can plot it. and it has magnitude, and it has direction. So let's go ahead and represent this scenario that we've got going on. So we're standing at the point 1, 1, and we want to travel in the direction of u, which will point in the direction 3, 4. So it'll basically point over here. Now the reason I'm not going to connect it is because what I'm going to do is I'm going to take 3, 4 and divide it, not 3, 4, it's the vector 3, 4, and I'm going to divide it by the magnitude of the vector 3, 4. That way I make it a unit vector, and again, price of gas, you always want to be per 1 gallon, you don't want it to be per 1.7 gallons. Now, the magnitude of the 3, 4 vector is 5, and so we're going to take 1/5 of both of the components, which will give us, if we leave these as decimals, 0.6 and 0.4. I'm sorry, 0.8. Okay, so now this is a unit vector, so if we travel 0.6 miles east and 0.8 miles north, if this were one of those hiking examples, then we would have traveled a total of 1 meter. But we're cutting across the plane. We're not going 0.6 units this way and then 0.8 units this way. So I can represent this a little bit more accurately now. So 0.6 units will put me right about here, and then 0.8 units right about here. So yeah, pretty close to what we had originally drawn. And this right here is the u vector. And I won't go ahead and write out the components because we've got it listed out here. Now, the gradient vector, which we said is a vector in its own right, the gradient vector right there, which is the vector 1 and 2.17, actually, relative to that point, points 1 unit over and 2.17 units up. So that gradient vector, grad f, which for convenience I'm going to write it with the del notation, it's a little bit more compact, I see that that one does not point in the same direction as u. And why should I really care? Because we never really were concerned about where this vector pointed. In fact, we never even thought about it as a vector. But there is an important relationship between these two things. In fact, we see that one thing that we can point out is that there's some angle, call it theta, between these two vectors, u and f. So theta is the vector, or is the angle between vectors u and grad f, or del f. So why do we care about that? Well, if we recall one of the properties, and we're getting really close to the punchline here. I know this sort of feels like it drags on, but there's a lot of development here and a lot of critical thinking going on that I think is important before stating the result. So if I travel in the direction of u, I want to know what's the relationship between u and grad f. So one important thing that we're going to recall at this point, that the dot product between two vectors from the law of cosines is equal to the product of their magnitudes multiplied by cosine of theta. So this comes from the law of cosines. Now how does that relate to what we have here? Well, here we have two vectors. One of them is u and one of them is grad f. So let's go ahead and write those in here. So grad f is like our vector x, and so this right here would be the magnitude of grad f. Y is like our u vector, and that's the magnitude of the u vector, multiplied by the cosine of theta. Now, the cool part here is that I get to choose which direction I travel in. So an important thing to note here is u is chosen. Right? You get to pick whether you walk that way or you walk that way, or you walk that way, or you walk that way. You can pick whichever direction you want to go in to represent your u vector, again, after it's unitized. But grad f is a fixed vector. And the reason we can think about it as a fixed vector is because it's determined fully by the point at which we're standing. So 1 and 2.17 happened because those were the components of f sub x and f sub y when we were standing at the point 1, 1. We plugged in 1, 1 into both of the partial derivatives, we got this vector. So del f is actually fixed at a given point. Okay, now that gradient vector, if you were to move over here, that gradient could say point out this way. The gradient itself is point specific, but it cannot change at a particular point. All right, so the reason we recall this is because under certain theta conditions, so if, and let me just go ahead and draw a quick graph of cosine theta, or the first 180 degrees, looks like this. So if theta is between 0 and 90 degrees, 0 degrees and 90 degrees, 0 inclusive, 90 degrees not inclusive, then one thing that we know is that cosine of theta is going to be positive. So if that's the case, then the largest that this dot product can ever be is when cosine theta is as large as possible. So recall that theta is just the direction that we move in relative to the gradient vector. So if, in fact, we go ahead and say that theta is equal to 0, when theta is equal to 0, cosine of theta is equal to 1, which is the largest possible cosine theta you can have. Positive 1 is the biggest, negative 1 is the smallest, 0 is, of course, the 0. So if theta is equal to 0 degrees, cosine of theta is equal to 1. And that means that if cosine theta is equal to 1, then we've maxed out this component, and so now the only result in that product, the only thing that result is dependent upon is the size of the gradient and the size of that u vector. Now here's another cool part. This is equal to 1 because we've made it the unit vector. So if this situation here pans out, then the directional derivative, f sub u, remember the change in f per unit change in the direction of u, f sub u at that point, AB, is simply going to equal the magnitude of the gradient vector. And this is the maximum possible directional derivative. In other words, if you move in the direction of the gradient vector, that is the largest possible slope that you can have. In other words, if this were a mountain, if we moved in the direction of the gradient vector, we would be traveling uphill in the greatest possible capacity. That is to say that we were traveling along the steepest part of that mountain. Now, if on the other hand, if theta is equal to 90 degrees, in other words, if we travel perpendicular to the gradient vector, either here, or to 90 degrees, there's a 90 degree angle, there's a 90 degree angle, then what we do know is that cosine of theta is equal to 0. And if cosine of theta is equal to 0, then that zeroes out the entire right-hand side. So that means that the change in f per travel in the direction of u, also written as f sub u of a comma b, is going to equal 0. So what this means is that there is no elevation change. So this could be used to answer questions about, well, in which direction do we travel in order to not affect our output at all? And if we travel perpendicular to the gradient vector, then we're not going to change the output value at all. And that's a pretty powerful result as well. Now, one final consideration is if theta is equal to 180 degrees, well, that means that at 180 degrees, cosine of theta is equal to -1. Is that -1 instead of +1 or 0? And so what that will do is we'll have the magnitude of the gradient vector multiplied by 1 multiplied by -1. And so that means our directional derivative, which is f sub u at the point a comma b, will be the negative of the magnitude of the gradient vector. And so that is as large of a negative value as we can possibly get out of cosine theta. So if that's the largest negative that we can achieve, and of course magnitudes aren't going to be negative, so this will tell us that this is the minimum possible directional derivative. So to put this in more contextual terms, this is the direction up here for theta equals 0 degrees, direction of maximal ascent or maximal steepness. The traveling perpendicular to the gradient vector will result in direction of 0 steepness. And if we travel opposite, in other words, the exact opposite direction of the gradient vector, then what we get is the direction of minimal steepness. Now, minimal, you have to be careful because the larger the negative is, the more minimal that is. Right? So large negatives are actually smaller than positives. So when we say minimal, we mean the largest negative value that we can generate. And so not only does that give us insight, and let's go ahead and just draw these here. So if the gradient vector is this guy here, and we travel in the direction of the gradient vector, there's our u, and this is del f, then we'll get the direction of maximal steepness. If we travel perpendicular to that vector, so if that vector points there, that's del f, then if we either travel here or here, such that that's a 90-degree angle, then we will get no elevation change at all. Now this should also make sense intuitively. When you travel the opposite direction of the gradient vector, then you're really just traveling with the same slope but in the opposite direction. So if the slope here is 500, then your descent will be -500 if you move exactly the opposite direction. And that's, of course, based on instantaneous rate of change. So here, if we travel this way, 180 degrees relative to the gradient vector, we will travel down the hill as fast as we possibly can. So let's summarize these things now that we have all the mathematics worked out. So we've already established that we can travel in whichever direction we want, denoted by the u vector. Then relative to the gradient vector f, gradient of f, now notice that this is coming from a textbook, they don't put the vector above here. It really should be there. And there's some angle right here between the vector that we're traveling along and the gradient vector. Now, if theta is equal to 0 degrees, we will get the maximum possible f sub u. So that means we're going to be traveling uphill in the maximal steepness direction. If we travel perpendicular, so pi halves, which is 90 degrees, or this negative pi halves, which is still 90 degrees, then what we're going to get is 0 f sub u. In other words, no change in our elevation. And if we travel opposite the direction of the gradient, theta equals pi, which is the same thing as saying, again, 180 degrees, then we get the minimum possible f sub u. It'll be negative, and it will be equal to the negative of the magnitude of the gradient. Then we're going to travel downhill in the steepest possible descent. And that's really it. That's the relationship between grad f and u, is what's happening in this little picture here. So all this development just justified what we just concluded. So here are those properties. If f is a differentiable function at the point a comma b, in other words, it's continuous, the limits exist on that interval, and the gradient vector is not the zero vector. So sometimes you will find that, for instance, if you're talking about a plane, then it doesn't really matter which direction, whether you, well, maybe not a plane. A plane isn't a super good example, but a flat surface, maybe one that looks like this, then its gradient in all directions would be zero, at all points rather. And so that means you're not going to get any elevation change, period. So that's all this is saying, is as long as it's not the zero vector. Then the direction of the gradient is, first of all, perpendicular to the contour of f. We'll talk about that in a second. As in the direction of the maximal rate of increase of f. That's the maximal steepness, direction of maximal steepness. The magnitude of the gradient vector, grad f, is the maximum rate of change of f at that point. So that just justifies what we wrote here, that the directional derivative, if theta is equal to 0 degrees, will be just the size of the gradient vector. So it's kind of a double whammy. If we compute the magnitude of the gradient vector, then that is the maximal possible steepness that we can gain. And then grad f itself tells us which direction that maximal gain is in. So pink vector, the direction, tells us direction of maximal gain. Length of grad f tells us how much elevation change we will get. That is, what is the change in f by traveling in the direction of u. And the magnitude of the gradient vector is large when the contours are close together and small when they are far apart. So what we're saying here is in the direction of, that it's perpendicular to the contour of f through AB. Why is that so? So if this is the point AB, and this represents the gradient right here, why are we saying that this is perpendicular to that contour? Well, to use a little bit of intuition, if you have a maximal steepness, then that means you're treading uphill as fast as you possibly can. That means you're going to make it to the next contour sooner than if you were to, say, travel this way. So this is going to take you a longer distance to get to that same contour than if you simply went directly perpendicular away. Because here the distances are growing kind of slowly, but if you move directly away at a 90-degree angle, then you're going to have maximal ascent. So the gradient vector is going to point perpendicular to the contour that you're currently at. Let's go ahead and apply this now. So consider a mountainous region, similar to the initial example we explored of hiking, modeled by this equation here. You are at the point 2, 3, give the unit vector and the directional derivative in the direction you would need to go in order to achieve maximal steepness, so maximal steepness uphill, minimal steepness, which is really maximal steepness downhill, and no elevation change. So step 1 is going to be to compute grad f at the point 2, 3. Okay, so here we are in our plane. We're at the point 2, 3, and we're trying to decide which direction are we going to go in order to climb to the top of the mountain. And in order to get this, we need the two partials. So f sub x is going to equal 200y cosine of x plus 20x times cosine of y. And f sub y is going to be 200 sine x minus 10x squared times sine of y. And those are our two partial derivatives. Now when we evaluate these two, so let's form the vector now, f sub x at the point 2, 3. So we're going to plug in 2 for x, we're going to plug in 3 for y, and we're going to do the same thing for f sub y to get that gradient vector. When we plug in 2 for x, and we plug in a couple more here, 2 for x, and we plug in 3 for y, then the vector that we're going to come up with is the vector negative 289, or approximately, and 176. There's a little bit of rounding there, but since those numbers are fairly large, those decimals aren't going to make too much of a difference. Now, in order to travel in the direction of maximal steepness, we're going to move in the direction of the vector grad f. Okay, but we said that in order to do that, in order to be able to compare apples to apples, in order to be able to describe the average rate of change per 1 unit in that direction, so negative 289, 176 is going to point a lot this way and a little bit down, so it's going to look something like that, and that's going to be the gradient of f. So we want to unitize that because this is a really long vector. This is actually grad f right here at the point 2, 3, but we want the unit vector version of it. So to get the unit vector, we have to take grad f and divide it by its magnitude. So we're choosing to go in the direction of the gradient because u is our choice. And if we compute the magnitude of that, taking the square root of the sum of the squared components, you get 338. So this is going to be negative 289, 176, divided by 338. And if we apply that division to both components, we're going to get negative 289, 338ths, and 176, 338ths. So that's now a unit vector. That vector is 1 unit long. And to compute the directional derivative, now here we already know that the directional derivative in the maximum direction, I'm going to call this u max, that's in the direction of the gradient, at the point 2, 3, we know that that's going to equal the magnitude of the gradient vector. But let's just go ahead and compute the directional derivative and show that that's what's going to happen. So we could just say at this point that we're going to gain 338 feet of elevation per 1 mile in the direction of the gradient. But let's go ahead and do this by taking the partials, negative 289 times how far we travel in the x direction. So we're going to actually lose elevation if we travel in the x direction, or in the positive x direction. So what are we going to do? We're going to travel opposite that direction so that instead of making this a negative term, we're going to make it a positive term. Plus we're going to gain 176 feet of elevation per 1 unit traveling north. And so we want to go north because that's going to help us gain elevation, 176, 338 miles in that direction to be exact. And not surprisingly, we're going to get 338 feet of elevation per 1 unit in direction of the gradient of f. So that's the maximal steepness that we can walk. If we go in the direction of the gradient, we'll be able to achieve the fastest change in elevation. To answer question B, in the direction of minimal, we want to move opposite the gradient of f. Now, how do you find that vector? Well, to find that vector, the opposite of the gradient of f is simply going to be the negative of the gradient of f. So if a vector points, say, if that's the vector 2, 3, then if you take the negative of those components, negative 2, negative 3, then that points 2 units left and 3 units down, which is still along the same line, but it's 180 degrees. So the negative gradient of f, which will just be positive 289 and negative 176. Now this is f. This is the change in f per unit change in the direction of what we'll call u min. So now we're going in a direction that is going to minimize our elevation. And we already know that this is just going to come out to be, the derivative will be negative magnitude gradient of f. But if we again piece it together like this, we'll We're going to lose 289 feet of elevation for every 1 unit we travel east. We're going to travel, and then we need to divide this. We need to make this the unit vector. So that's just going to be 289 divided by 338 and negative 176 divided by 338. Its magnitude won't change, it just points the opposite direction. Its length stays the same. So now we're going to go positive units in that direction. You can see that this is going to maximize our negative because now we're traveling in the direction of where our elevation will drop the most. So there's a little bit of intuition there as well. Plus we're going to, this is a positive 289, excuse me. But our negative, darn it, this is actually negative here. The only thing that changed is the component of our vector. And now we still gain 176 units. This is still the gradient, the change in f per change in y, but we're going to move opposite the direction of that, where that positive change occurs. Negative 176 338ths of a mile to be exact. And believe it or not, this is going to come out to negative 338 feet per 1 unit in the direction of the opposite of the gradient. So we just see that the two values are going to be opposite one another. All we really had to do was know what the magnitude of the gradient vector was, and we didn't have to compute the whole formula for directional derivative. Now finally, and lastly, if we move perpendicular to the gradient vector, which could be either that way or that way, we're going to have zero elevation change. Okay, so if this is grad f, how do we find a vector that is perpendicular to our current vector? Well, two vectors are going to be perpendicular if their dot product is 0. So if I take the gradient vector, which is fixed at negative 289 and 176, so it actually points the opposite direction here. So if we go that way or that way, such that the angle here is 90 degrees, we're going to get no elevation change. So what we want to do is we want to find a vector such that when we take, if this is the vector xy, then if we take the dot product between negative 289, 176, and xy, that if they're going to be perpendicular together, to one another, then we should get a 0 dot product. And so that will be negative 289x plus 176y equals 0. And now we just need to find a value of x and y that will satisfy this equation. So if you solve for y in this equation, you get y equals 289 over 176x. So as long as you pick any value of x that as long as y is 289 176 of that value, so if I let x equal 176, then that means y will be 289 over 176 times 176, which will be 289. So that would be the vector that would be one vector that would be perpendicular to the gradient. So our u vector then will be this vector that is perpendicular, 176 divided by 289, sorry, not divided by, the vector 176, 289, divided by the magnitude of 176, 289, and that's still 338, so we'll have the vector 176, 338, and 289, 338. Lastly, we just need to show that the directional derivative by moving in the direction of u, of this new u, which we'll just call u0, to say that there's not going to be any change in f. Well, we know that this is supposed to be 0 based on the information that we put together, but let's just calculate the directional derivative. So we lose 289 feet of elevation for every 1 mile we travel east, but we're going to travel 176 338 miles in that direction. Plus, we're going to gain 176 feet of elevation if we travel, for every 1 mile we travel north, but we're going to travel 289 338ths of a mile north. And if you put these two things together, not surprisingly, we are going to get 0. And so that again will just justify that moving perpendicular to the gradient. Now you could have picked any value of x here. This just made it really easy. Choosing 176 for x allowed those to cancel out. I didn't have ugly fractions to deal with. Until I had to normalize or unitize the vector, then I had to deal with some pretty ugly fractions. So that's it. So the gradient vector is this beautiful thing that tells us the direction that we need to move in order to get maximal ascent. And this is used very often in applications like in machine learning and neural networks. Something called gradient descent is something that allows us to minimize cost functions. So it's very important stuff, and we're going to be using this more in the future.